2020 IEEE 40th International Conference on Distributed Computing Systems ICDCS Blockchain-based auditable access control for distributed business processes. Abstract. The use of blockchain technology has been proposed to provide auditable access control for individual resources. However, when resources are owned by a single organization, such expensive solutions may not be needed. In this work, we focus on distributed applications such as business processes and distributed workflows. These applications are often composed of multiple resources services that are subjected to security and then access control policies of different organization domains. Here, blockchain can provide an attractive decentralized solutions to provide auditably. However, the underlying access control policies may be overlapping in terms of the component conditions rules, and simply using existing solutions would result in repeated evaluation of users' authorization separately for each resources, leading to significant overhead in terms of cost and computation time over the blockchain. To address this challenge, we propose an approach that formulates a concentrate optimization program to generate an optimal composite access control policy. This policy is in compliance with all the local access control policies and minimize the policy evaluation cost over the blockchain. The developed smart contract can then be deployed to the blockchain and used for access control enforcement. We also discuss how the access control enforcement can be audited using a game theoretic approach to minimize cost. We have implemented the initial prototype of our approach using Ethereum as the underlying blockchain and experimentally validated the effectiveness and the efficiency of our approach. Index terms: blockchain, XACML, business process, access control, workflows. Introduction. The emerging cloud edge computing infrastructure has developed of next-generation internet-centered distributed applications that are autonomous, cooperative, adaptive, evolvable, emergent, and trustworthy. Such internet-centered distributed applications include business processes (BPs), distributed workflows, and web service mashups. First, second, and third. Since these applications are architected and developed using resources and services that may belong to different organization domains, access to the underlying resources and services is governed by security and access control policies of the respective resources owned domains. Fourth and fifth, access control ensures that resources are used only according to the access control policies defined by the resources owners. Typically, resources are protected by access control system deployed within the organization. However, this does not directly provide auditability of the access control enforcement, and also cause a significant organization burden since the organization now need to bear the overhead of configuration, deployment, and management of the system, along with the hardware, software, and manpower cost. A recently proposed alternative solution is to use blockchain technology for access control. The basic idea here is to transform the access control policy evaluation process into a completely distributed smart contract executions. With this transformation, the access control enforcement is the same time outsourced and auditable. However, existing solutions 6, 7 focus on the access control policy for the individual resources and encoded the access control policy for each resources within a single smart contract on the blockchain. The smart contract then need to be executed in order to return the access decision for the particular resources. This is quite expensive. If all of the resources are within a single organization, issues of trust do not exist. Alternative solutions exist, such as temporal flows, to provide auditably at lower cost. On the contrary, distributed applications, including BPs and distributed workflows, are composed of multiple resources services that are subjected to the security and access control policies of different autonomous original domains. Consequently, each of these services in the BP will have its own access control policy and the corresponding smart contract to evaluate it. Here, utilizing blockchain is very attractive since it provides auditably in a decentralized environment. However, directly using existing blockchain-based solutions to manage access control for such distributed applications requires evaluating the user's authorization separately for each service that needs to be accessed. This may have a significant overhead in terms of cost and computation time for blockchain transactions, especially when individual domains access control policies are overlapping. The set of individual access control policies of all services involved in the BPs is likely to have some common causes. As shown in example 1, if each of the smart contracts evaluate the access control policy of every service is executed separately, the common clauses condition will be reevaluated by their respective smart contract as many times as they appear in the individual access control policy as illustrated in example 1. This kind of reevaluation causes cost of evaluation to increase significantly for a blockchain-based access control system. This is due to the increase of computation and storage requirement, resulting in an increased transactions fee being charged by miners. Example 1. Consider distributed data analytics workflow of supply chain monitoring application tool that collect, integrate, and analyze real-time data from different data sources, emerging reporting systems, social media, and IoT devices, sensors, environmental, traffic, chemical, fire detection, surveillance cameras, etc., etc. This data analytics workflow is depicted in Figure 1 and instantiated dynamically in response to highway accident in which a tractor trailer carrying several drums of liquid acetone overtuned and exploded, generating a smoke plume that spread a large area. Now consider the access control policies of some of the web services used in the emergency management workflow. Traffic congestion monitoring service. This service takes feed from the surveillance cameras and road intersections and analyzes them to determine traffic congestion. The surveillance cameras are owned by Smart City Project Authority, which requires that only offers from the Transportation or Policy Department can access their camera feed. Therefore, traffic congestion monitoring service can only be accessed by officers from the Transportation or Police Department. Plum modeling. This service takes the sensory data observation in the vicinity of the incident site, and it identifies the risk areas that could be affected by the plume. This sensor data comes from the devices installed by the Environmental Protection Department, and they allow access to only officers of enlist grade 18 from the Environmental or Transport Department. Therefore, plume modeling service can only be accessed by officers of enlist grade 18 belong to the Environmental or Transportation Department. Cargo truck location. This service is used to distribute the location of all cargo trucks of supply chain monitoring company. According to the policy of the supply chain monitoring company, location of each trucks can only be accessed from within the same city by any officer from the Environmental, Transportation or Police Department. Therefore, cargo truck location service can only be accessed from within the same city by officer from the Environmental, Transportation or Police Department. The evaluation or common conditions. You consider an officer of grade 18 from the Transportation Department who is in the city and want to execute the emergency management workflow. Clearly, the condition that access subject belongs to the transportation department get evaluated again and again. For each the affirmation the web service before the officer is granted access to execute the workflow, even if access is denied for the subject. Still, the condition of police and the environmental department are re-evaluated across the two services. A composite access control policy is hence needed to reduce the cost of evaluation from blockchain-based success control system. By removing these repetitive evaluations, such a plan should be designed keeping in view the access control policy need of the particular BP in question, and it should be optimal with respect to cost in the form of mining fee incurred due to blockchain transactions. This is precisely the problem that we address in this work. Our key contributors are to propose the approach that formulate a constraint optimization problem to generate a composite access control policy for BP that encapsulate the local access control policies of component services and minimize the policy evaluation cost over the blockchain. Present game theoretical approach to reduce the cost of auditing the access control enforcements. Implement and experimentally validate the proposed approach using Ethereum testnet recovery. Preliminaries. Distributed application requiring access to resources from different autonomous original domains can be represented as distributed BP workflows. Typically, the access control policy of original government governing these resources are specified XHTML. We now present a brief review of BPs and the XHTML business process. Business process is a composite of iterative activities materialized in the form of web service to achieve a well-defined business outcome. 9. While the workflow in example 1 can be naturally expressed in forms of a distributed business process, it is quite complicated and it would be difficult to clearly explain all of the steps of the proposed approach given the space in limitation. Therefore, for the rest of the paper, we consider a simple alternative example in the university context which serves to comprehensively illustrate the access control requirement in a multiple organization environment. So note that all of the work applies in general to any distributed workflow. Example 2. Consider an assignment graded BP shown in figure 2 in a virtual university environment where 3 universities, LUMS, Rutgers, and Cardiff, collaborate. An instructor from the university can teach courses to students of the universities. The first step in this visual business process is downloaded the assigned of all the students in the course from the learning management system LMS of the respective universities. The LMS universities LUMS, Rutgers, and then Cardiff are access to the downloading the assignment using the download LUMSA assignment, download Rutgers assignment, and the download Cardiff assignment service respectively. After downloading these assignments, need to transfer to server machine on the which AutoGrader application runs. There are 2 servers, Codex and Rustem, each of which can be used for running auto-grading service. Codex is the first choice, which is available 90% of times via transfer to Codex services, which the remaining 10% of the times Rustem is used via transfer Rustem service. After grading assignment, the score needs to be uploaded to the grade management system. Jambel over Rums, Sakai over Reuters, and Sims of Cardiff using the LUMS marks, Umlaut Reuters marks, and the Umlaut Cardiff's marks service respectively. Finally, the students are notified of their grade. The email notification service notify via email is selected 80% of the time, while SMS notification service notify via SMS is selected 20% of the time. The probabilities in Figure 2 represented the likelihood of the service being called based on service availability statistics and or execution passes. The access control policies of some of the services used in example 2 are given in Figure 3. XACML. The extensive access control Markov language XACML is published standard that defines first, a declarative fine-grained attributed-based access control policy language. Second, an architecture, and third, processing model describing how evaluate access requests according to the rules-defined policies. An XACML policy consists of a target, a rule set, and a rule combining algorithms. In XACML, the authorization of subjected over resources for given action are specified as rules. A rule is an access control policy is comprised of conditions which defines the requirement of specific attribute that must be present in the access request or could be inferred derived from the access request. We consider three types of conditions: atomic condition, composite condition, and then permit deny condition, and each of the defined below. Definition of atomic condition. Atomic condition is a Boolean expression, and then that compares the value of an attribute or functions over attribute to another attribute or value. Definition. Composition condition. A composition condition is a Boolean expression over atomic conditions and or other composite conditions which can be joined by conjunction or disjunction. This definition: permit and deny condition. Permit and deny condition is a composite condition that specifies the resources as well as actions or the resources of which the permission is granted or denied. Definition for authorized rule. The authorized rule can be represented a direct acyclic graph GVE, where V is a set of vertex corresponding to either permit and deny condition, or atomic condition or composite condition. V is a set of ordered pairs representing directed edges between vertex in V. General represent of the access control policies of downloading ROM assignment sample service of example 2 is shown in listing 1, and then each corresponding graph shown in figure 3. In the policy graph of downloading ROMSA assignment service is a permit condition that authorizes service subject satisfied by the predecessor condition for the actions downloading assignment on the resources ROM LMS. The composite condition is supervisor course is a conjunction of two atomic conditions is supervisor. In the instructor referred to by instructor number must be the supervisor of the requesting student referred to by the roll number. Teaches in integer number. Course code. The instructor teaches the course referred to by a course code. There are two other atomic conditions. Is a PhD student, roll number, university ID. The requesting student is a PhD student. Download ROMSA assignment. A PhD student having a CGPA of at least 3.5 can download assignment of his or her supervised course. Supervisor's course. Instructor teaching the course should be supervisor of the requester. Download Reuters assignment. A graduate student can download assignment of he or her supervised course. Supervisor course. Instructor teaching the course should be supervised of the requester. Download Cardiff assignment. A senior PhD student can download the assignment of a course that she or she has studied earlier. has high CGPA, roll number, university ID. The requesting student has a CGPA of at least 3.5. Problem statement: considering the access control policies associated with the underlying of web services, we can formally define distributed BP as follows. Defined file business process. Business process is denoted by a graph BP STUDUQ, where S is a set of web services represented as vertex of BP. TSS is a set of all edges in BP. UT 0.1 is the function defining probabilities of edges in T. Q G1 to Gn, where Gj equal Vj Ej is a graph which encoded the rules based on definition 4 and represented the access control policies of services as J. We control a service cloud environment where BPs are composed using web services from the multiple organizational domains as depicted in Figure 4. The cloud service provider hosts such BPs and also ensures that users executed the BPs satisfy the access control policies of the underlying organization domains. The cloud service provider has knowledge of the access control policies of the organizational domains and then use this knowledge to develop optimal composite access control policy for a BP and deploys it over the blockchain as one or more smart contracts to ensure auditability. Here we assume that the access control policies of these organizations do not include sensitive information and are publicly available. To ensure access control, the objective is to deploy one or more contracts containing all the authorization conditions or underlying web services on the blockchain. However, deploying single unified smart contract by taking union all of the control policies may not always be optimal in terms of blockchain cost. Therefore, the unified access control policy, denoted by G, can be partitioned in many ways instead of the fragment, where each fragment contains one or more authorization conditions. We refer to such a partition of G as a composite access control policy F1, F2, Fn. The structure of the BP business process is determined which partition of unified policy may result in minimal cost of deploy and evaluation. Formally, the optimal composite access control policy generated problem can be defined as definition 6. Optimal composite policy generation problem. Given BPs, find the partition of F1, Fm of the global unified access control policy G such that sum of the cost of the smart contract corresponding to all fragments in F is minimal over the partitions of G. Proposed approach. The proposed approach for finding the optimal composite access control policy consists of 5 major components as depicted in Figure 4. For a given BP and the associated access control policies, the composer generates the composite access control policy, which is an optimal partitioning of the unified access control policy. The translator is responsible for transforming the composite access control policy into one or more smart contracts. The deployment engine deploys these smart contracts over the blockchain, which are executed to determine the access control decision for any given user request. The composite access control policy may split the individual service providers' policy into multiple smart contracts. Moreover, a single smart contract may be part of the multiple service providers' policies. The deployment engine keeps a mapping between each web service and the set of smart contracts satisfying each access control policy. The deployment engine also registered the associated smart contract for each web service which corresponding service provider. The service provider may verify that the associated smart contract satisfies its local access control policy. The BP manager (BPM) is responsible for evaluation and enforcement of the composite access control policy through smart contract. The adaptation engine monitors change in the service providers policies and triggers revision of the composition access control policy within minimum changes. We now discuss the proposed approach in detail. Optimal policy composition. The composer combines the multiple service view of the access control policies Q. For all services, S is a BP to give a global unified view of the access control policy. To do this, for this step is to merge all the access control policies of individual web services in the BP to obtain the global mediated access control policy G. Note that G should not have any duplicated conditions, while all the conditions of each individual access control policy in Q are satisfied. Next, the composer needs to partition G into composite access control policy such that the cost of deployment and evaluation on the blockchain is minimal. To find the optimal composite access control policy, the composer needs to estimate the combined cost of the deployment and the evaluation on the public blockchain. This cost depends on size and the number of fragments of the partition and the probability that a smart contract corresponding to each fragment gets executed. Given the structure of the underlying BPs, the overall sequence of steps given in algorithm 1, we now explain each step. Global Mediated Access Control Policy. The Global Mediated Access Policy (GVE) is simply the union of all of the underlying access control policy graphs GJ, along with a sync node, one for permit and one for deny. All of the permit conditions are connected to the permit sync node, which all of the deny conditions are connected to deny sync node. The step of generate the global mediated access control policy is given in algorithm 1, lines 1 to 8. Figure 5 depicts the global mediated access control policy graphs shown in the outmost dashed rectangular box for the business process in the figure 2. This global mediated policy also includes the assignment download policies of figure 3 depicted in bold. Optimal composite access control policy. The composite access control policy can be generated in multiple ways from the global mediated access control policy G. In order to find the optimal composite access control policy, we need to decide whether to keep each of the conditions in G as an independent smart contract, or make a part of smart contract of composite conditions. This decision needs to be made for each condition G, keeping in view of the contribution to the overall cost may be made by this decision. The select of condition which incur the least cost will be considered as the optimal composite access control policy by G. Example of possible composite access control policy is shown in figure 5. Which conditions selected for deployment as a separate smart contract are shown in small rectangular boxes, while those